Hello everyone, I am Abhishek HR. Welcome back to the online session on dynamics of machines. In the previous session, we learnt about the conditions of critical speed. Means critical speed of shaft, lightweight shaft without damping and critical speed of shaft with damping. Now in today's session, we are going to solve some numerical problems based on the critical shaft concept. A steel shaft simply supported in bearings 50 mm diameter. A steel shaft simply supported in bearings 50 mm diameter and 1.5 meter long. 1.5 meter long carries a solid rotor of weight 1600 Newton at its center. Find its critical speed if E is equal to 200 giganewton per meter square. So it's a very simple problem. Here we are going to find the critical speed of the shaft. So as you all know, we should first read the problem statement carefully, because from the problem statement always we'll get some hint or some data so that we can find out the required parameter. So from this statement, one thing, a steel shaft simply supported means it is a simply supported beam like structure, isn't it? Simply supported in bearings means there is a shaft, it is supported by the two bearings. And 50 mm diameter means the diameter of the shaft. How much? 50 mm. 50 mm. It is in mm converted into meter. So it will become D is equal to 0.05 meter. 0.05 meter. Next, and 1.5 meter long, 1.5 meter long carries a solid rotor of weight 1600 Newton at its center. Here we have two data here. One is 1.5 meter long means length of the shaft. How much? L is equal to 1.5 meter. 1.5 meter. Solid rotor of weight 1600 Newton at its center, which means 1600 Newton is what? That is the weight of the rotor or the disc. How much? 1600 Newton. So it is in Newton. In some of the problems they may give in kg also, but here we have Newton. And find its critical speed if E is 200 giganewton per meter square. E is given 200 giga means how much? 10 to the power of 9. 10 to the power of 9 Newton per meter square. Newton per meter square. Now we need to find out the critical speed. While deriving the condition of the critical speed, we have seen one condition, that is omega c is equal to omega n. So from this condition we have a formula, nc is equal to 1 by 2 pi into square root of g by delta. This is a standard formula to find the critical speed. Now from this we can find out the critical speed. So 1 by 2 pi into square root of g by delta. G is known value, that is 9.81. Delta, that we don't know. Delta we have to find out. But there is a hint in the given problem, that is simply supported, right? So for the simply supported beam we have a formula, that is delta is equal to W into L cube divided by 48 E into I. W L cube divided by 48 into EI. This is the a standard formula for the simply supported beam. Here weight we know how much it is, 1600 Newton. Length also we know, that is 1.5 meter. 48 into E is also given in the problem, 200 into 10 to the power of 9 Newton per meter square. And I, with respect to simply supported beam, for I is pi into d to the power of 4 divided by 64. So using this we can find out the I value. Now use this formula, delta is equal to W is how much, 1600 into L is 1.5 meter whole cube divided by 48 into E is how much, 200 into 10 to the power of 9 Newton per meter square. And I is what, pi into the diameter of the shaft is how much, diameter of the shaft 0.05 meter, 0.05 power 4 divided by 64. So if you simplify this, you will get 1.833 into 10 to the power of minus 3 meter. 1.833 into 10 to the power of minus 3 meter. Delta is equal to 1.833 into 10 to the power of minus 3 meter. This is delta value. Now we have to find out the critical speed. So NC is equal to 1 by 2 pi into square root of G is 9.81 and delta is how much, 1.833 into 10 to the power of minus 3. So NC is equal to 698.6 RPM. 698.6 RPM. This is the critical speed that we have to find out from this statement. This is in RPM, but according to this formula, if you simplify this answer, you will get the answer in RPS. So if you multiply with 60, it will be converted to RPM. So our final answer is NC is equal to 698.6 RPM. Now we will see the second problem. A rotor of mass 12 kg is mounted midway on a 25 mm diameter horizontal shaft supported at the ends by two bearings. A rotor of mass 12 kg or the disc, the mass of the disc or mass of the rotor is 12 kg, is mounted midway on a 25 mm diameter horizontal shaft. The diameter of the shaft, how much? 25 mm. Supported at the ends by two bearings. The span between the bearings is 900 mm. Length of the shaft, how much? 900 mm. Because of some manufacturing defect, the CG of rotor is 0.02 mm. That is eccentricity, 0.02 mm, small e, eccentricity, away from the geometric center of the rotor. If the system rotates at 3000 rpm, determine the amplitude of the steady state vibration. Amplitude of steady state vibration. So from the given problem, rotor of mass M is given, mass M is 12 kg and diameter of the shaft D is 25 mm, 25 into 10 to the power of minus 3 meter. Then the span between the bearings is 900 mm. Length is how much? 900 mm. L is equal to 0.9 meter. Because of some manufacturing defect, the CG of rotor is 0.02 mm, which means small e is 0.02 mm. So 0.02 into 10 to the power of minus 3 meter. Because of some manufacturing defect, so that is why the eccentricity is going to occur in the disc. If the system rotates at 3000 rpm, so n is given 3000 rpm. This is not the critical speed, this is the rotational speed or the operating speed, that is 3000 rpm. Determine the amplitude of steady state vibration. So from the conditions of the critical shaft, we know one formula, that is y is equal to omega by omega n whole square into e divided by 1 minus omega by omega n square. This we can also write it as y is equal to e by omega c by omega whole square by whole square minus 1. So we can write the expression like this, e by omega c by omega into whole square minus 1. Further we can write it as y is equal to nc by n whole square minus 1. So how we got this? From the omega, means omega means what? 2 pi n, right? So we have the operating speed n and this is nc, that is the 2 pi nc. So 2 pi will get cancel, so remaining terms are nc by n, so that is whole square minus 1. Now for this, now from this I can calculate the amplitude of steady state vibration. But here I know the value of n, but I don't know the value of nc. So from the previous problem, so we know that nc is 1 by 2 pi into square root of g by delta. Here also we don't know the value of delta. Again we need to find out the delta. So as per the problem, see here, mass of 12 kg is mounted midway on a 25 mm diameter horizontal shaft supported at the ends of two bearings. It is nothing but the simply supported beam only. So for the simply supported beam, we know the standard formula, that is delta is equal to W L cube by 48 into EI. So that is nothing but delta is equal to W, but here we have mass 12 kg. The formula, in the formula it is W. So W is equal to m into G. 12 into 9.81 into length is how much? 0.9 cube divided by 48 into E is how much? It is, so it is not given in the problem, so consider it as E is equal to 200 GPa. So 200 into 10 to the power of 9. 200 into 10 to the power of 9. I is pi d to the power of 4. D is how much? 25 into 10 to the power of minus 3 whole power 4 divided by pi d 64. So we'll get delta 4.66 into 10 to the power of minus 3 meter. Now from the delta we can calculate the NC. So here 1 by 2 pi G 9.81 divided by 4.66 into 10 to the power of minus 4. So we'll get NC 1385.5 RPM. So if you do the calculation in your calculator, so we'll get the answer 1385.5 RPM. It is in RPM. While calculating, you will get the answer in RPS and multiply that answer with 60, so you will get in RPM. Now I got the two values NC and N. Now I can easily find out the amplitude of the steady state vibration. So Y is equal to, E is how much? 0.02 into 10 to the power of minus 3, and NC is how much? 1385.5, and N is 3000 RPM. So if you simplify this, so we'll get 0.0254 into 10 to the power of minus 3 meter. 0.0254 into 10 to the power of minus 3 meter. So I'll just repeat the steps. So from the problem statement, we have extracted the data like mass, diameter of the shaft, length of the shaft, and eccentricity, and the rotational speed, that is 3000 RPM. So from this I have to calculate the amplitude of the steady state vibration, but according to the formula it is NC by N. So I have the value of N, but I have to find out NC. So to find out NC, it is the formula NC is equal to 1 by 2 pi into square root of G by delta. But here we don't know the value of delta, that is deflection. So since we know that from the problem, from the given problem, we know that it is the problem on simply supported beam. So for that we have a standard formula, delta is equal to W into L cube divided by 48 into EI. Here we know the value of W, L, E and I. So for this, if you calculate, so we'll get the deflection 4.66 into 10 to the power of minus 3 meter. So by using this delta value, so I can find out the amplitude of the steady state vibration. So Y is equal to E by NC by N whole square minus 1. So in NC 1385.5, so that we have got from this, and N, it is given in the problem if the system rotates at 3000 RPM. So if you do the calculation, we'll get the amplitude as 0.0254 into 10 to the power of minus 3 meter. So this is how we are going to calculate the amplitude of the steady state vibration. See, while deriving the condition in critical shaft, so we got the expression like Y is equal to omega by omega n whole square into E divided by 1 minus omega by omega n whole square. So from that expression, or from that the derived expression, we have modified it. We have just modified for our convenience to calculate the amplitude of the steady state vibration. So this is how we are going to calculate based on the critical speed. Now we will see the third problem. A shaft carrying rotor of weight 450 Newton and eccentricity is 2.54 mm rotates at 1200 RPM. Determine, first one, steady state amplitude, second one, maximum whirl amplitude during startup conditions of the system. Assume the stiffness of the shaft as 36,000 Newton per meter and the external damping ratio as 0.1. So from this problem, here we have to find out the amplitude of steady state and the amplitude while in operating condition. So from the problem we have the data. Carrying rotor of weight means the weight of the rotor is given how much? W is equal to 450 Newton, 450 Newton, and the eccentricity small e how much? 2.54 millimeter. So 2.54 into 10 to the power of minus 3 meter. Now we have to find out the steady state amplitude. So first one, steady state amplitude. So for this we know the formula, y is equal to E into omega by omega n whole square divided by 1 minus omega by omega n whole square. Now for this we need to find out the amplitude, but here we have two parameters, omega and omega n. Omega n is what? Square root of k by m. So here the stiffness of the shaft is given 36,000 Newton per meter, and the mass, but it is in Newton, so we can write it like this, omega n is equal to square root of k by m. Since the weight of the rotor is in Newton, so it will become square root of k into g by w. So omega n is equal to square root of 36,000 into 9.81 divided by 450. So we'll get omega n 28.014 radian per second. So this is what omega n. Now we need to find out the omega. So for that, omega is equal to 2 pi n by 60. So 2 pi into n. So the n is how much? So here for n, it is given in the problem, rotates at 1200 rpm. So 1200 by 60. So if you do the calculation, you will get 125.64 radian per second. So this is what the angular speed, omega, 125.64 radian per second. So now here we want the frequency ratio, omega by omega n. So if you do omega by omega n, 125.64 divided by 28.014, so we'll get 4.486. 4.486. Now substitute this value in the expression of the amplitude. So we'll get y is equal to E is how much? 2.54 into 10 to the power of minus 3 into omega by omega n is how much? 4.486 whole square divided by 1 minus 4.486 whole square. So is equal to minus 2.67 into 10 to the power of minus 3 meter. So next we need to find out maximum whirl amplitude. Maximum whirl amplitude. So for this means when we come for the maximum whirl amplitude, so damping will come into picture. So for that we know the expression E into omega by omega n whole square divided by 1 minus omega by omega n whole square into whole square plus 2 zeta into omega by omega n whole square. So this is the formula, y is equal to E into omega by omega n whole square divided by square root of 1 minus omega by omega n whole square into whole square plus 2 zeta omega by omega n whole square. Now substitute the value here. So y is equal to, E is how much? 2.54 into 10 to the power of minus 3 into omega by omega n is 4.486 whole square divided by square root of 1 minus 4.486 whole square into whole square plus 2 into zeta is how much? The damping ratio 0.1. 0.1 into 4.486 whole square. So if you do the calculation, if you simplify this, so we'll get y is equal to 2.67 into 10 to the power of minus 3 meter. 2.67 into 10 to the power of minus 3 meter. So this is for maximum whirl amplitude. What we have calculated for the first condition, that is steady state amplitude, that is for the stationary condition. For that we got the amplitude as minus 2.67 into 10 to the power of minus 3 meter, and for the maximum whirl amplitude we got 2.67 into 10 to the power of minus 3 meter. So like this we can solve the problems on critical shaft. So as per this, so they are asking to find the steady state amplitude and maximum whirl amplitude, so during startup condition of the system. So we have calculated for the two conditions. So one is for the steady state condition. For that we have considered the formula y is equal to E into omega by omega n whole square divided by 1 minus omega by omega n whole square. So for this omega and omega n, we know the formula, that is k by m. So using this formula I have calculated the omega n. So I got omega n value as 28.014 radian per second. Now after this I know the rotational speed, that is n 1200 rpm. So for that w is equal to 2 pi n by 60. So 2 pi into 1200 by 60. So we got omega is equal to 125.64 radian per second. So just to simplify our process, so I got the value of the frequency ratio, that is omega by omega n, as 125.64 divided by 28.014. So we get 4.48 radian per second. So if you apply this here in the steady state amplitude formula, so we'll get the answer y is equal to minus 2.67 into 10 to the power of minus 3 meter. So for the maximum whirl amplitude, y is equal to E into omega by omega n whole square. But here we are going to consider the damping ratio because it is for the maximum whirl amplitude. So from this we'll get the amplitude as minus 2.67 into 10 to the power of minus 3 meter. So like this we can solve similar problems based on these two conditions. First thing is you need to analyze the problem statement and you have to extract the data in the given problem. And in some of the problems they may give some hint, means like just we have solved the problems on the simply supported, means a shaft is supported between two bearings. So like that they will give hint in the problem. Using that hint you can solve the problem easily. And formulas are very important, so be careful about the formula, and the data given in the problem is always in mm, so you should convert into meter then apply it into formula, so you will get the answer. Thank you.